Okay, so what we're going to try to do here, and of course it'll always does that. Make sure everything is going to be in order here. We're going to turn on a little bit of the lights here for you. All right, can you see the board better when it's all dark like that?
Yeah.
Alrighty, so what I want to do is we're going to try to look at some of these quadratic integrals. And I have to do some weird stuff here like that. Okay. So I might have you do a quick little, well, no, we don't have to do that warm up. We're going to try to do something like this as an example here. I have 1 over 4x squared now plus 9 squared dx. Okay? So, we're just going to try to talk a little bit about some of these quadratic integrals. Okay? And let's see how you handle some. Let me go back here really quick. Okay. All right, some quadratic integrals. Now, you might say to me, this particular integral, how are we going to handle this? Down here, you have a what? This is a quadratic. You guys okay with that? However, you may want to note that trigonometric substitution. Now, this is in trig sub. So what they want you to do is use that techniques in trig sub. Does that make some sense? Okay, so I just want to let you guys know. Now, that's a quadratic. Now, there's a couple of ways to do this, because in trig sub, you might say, oh, Mr. Judge, we have various cases, right? We got x squared minus a squared. We have a squared minus x squared. We have x squared plus a squared now, where a is positive here. Okay? Okay, you guys okay with that? So you might say, oh my God, they want me to do a trig sub, but I don't even have a radical. Well, the truth is you can still do a trig sub even if it doesn't have a radical, in all honesty. Okay? So let's kind of go through how that might be done, because I can actually think of a couple of ways. Going back to what we already did in the past, I want you guys to notice something here about what you have. Okay? You might say, can I see this as 2x squared plus 3 squared squared dx? Okay, you guys see my point? And in this case now, I don't know, we'll say, look at this, and then look at what? This here. Okay, where we're going to have to try this out, but to be u sub first. We're going to say, here's a u substitution first, where u will be 2x. So that means du is 2 dx, or it really means dx will be du over 2 here. Okay, so by doing that u sub to start, you start to see that this looks like it's u squared now, plus 3 squared squared, and dx is that du over 2, which means we factor out the 1/2, and then we have u squared plus what? That 3 squared du. Okay, so far so good? All right, you guys see what I'm saying? And then you say, but I don't have a radical, because this looks like now, it looks like whatever this is. Whatever case that was. Now, what does your book say? What case is that? Square root? Case number what? A squared plus x squared. Is that right? What case is that? This is in our book. I think this is case 2. Is that true? Is that right? Well, then here, this is also going to be thought of as case 2 here. So even though you don't have that radical, and you say, well, that kind of looks like these quadratics, it does. They intend for you to use, in this section, they intend that you actually use what? Yeah, they intend for you to use trig sub, because it's in the section. So, okay, now, what does case 2 say? What does u have to be again in case 2? Do you guys remember? You need this value called a, is that right? So this is 3 what?
Squared.
What is that? What does case 2 say? Is it what? We didn't work on case 2? Did we do, I thought we did case 2. We did case 2, maybe the first day. Right? So what do you let in case 2? What do you let? Isn't that 3 what? Tangent theta. Right? 3 tangent theta. So what does that mean then? What is du? What's du? Anybody remember? What would du be? Well, what's the derivative of tangent? So it's 3 secant squared theta d theta. Is that right? Okay, you guys okay with that one? Now, you might say, okay, but Mr. Judge, what do I do with my radical? Remember in trig sub, you had a radical to replace? Because it was always what? It was always that radical. And you use the Pythagorean theorem and all that. I mean, not the Pythagorean identity, and then you replace the radical with the appropriate trig substitution as well. But you say, but there is no radical. So then what do you do when there's no radical? Well, what you do is what you've always done. You go and say, what do you mean? Well, you're replacing u. What does u really become here? You guys remember? That's going to be 3 tangent theta what? Squared. Is that right? Plus 3 squared, and then that whole thing is squared. But du is actually 3 what? Secant theta d theta. Is that right? So double check, ladies and gentlemen. Okay? Isn't that what's going on here when I did the trig sub? I know there's no radical. So we have the 1/2 now, and we say, what does this give us? It's going to give us 3 secant squared theta over what? I'm going to say 3 squared tangent squared theta, right? Plus 3 squared what? By itself with the d theta. So double check if I did the case 2. I know I'm not replacing a radical, but there is no radical. And then what could you guys do with this 3 squared constant? Okay, see that 3 squared? What could you do with that? Can't we factor out by algebra? Right? Right? We get what? 1/2 now. I'm going to integrate. This will be now what? 3 secant squared theta d theta, secant squared theta now. And then that's going to be a 3 squared tangent squared theta plus 1 d theta.
On the previous step, you put it squared, but you already distributed the squared.
Oh, sorry. I apologize. Let me go back. I messed up with the algebra. I'm thinking of this email. There's an issue here. Okay? And let me go back here. Let me do every step of the algebra. There's a square there. Is that right? So what does that actually mean here? That means this. I can factor out the 3 squared. However, what? I have a squared here, I believe. You guys okay with that? Right? So what does that give us then? If I focus on that, that means a couple of things. The numerator is still 3 secant squared theta, right? And then your denominator, ladies and gentlemen, is going to be what? That's going to be, if I distribute, isn't that 3 to the 4th? And then what's tangent squared theta plus 1? Do you guys know what tangent squared theta plus 1?
Or secant squared?
Isn't that secant squared theta? So let me actually do it this way. Let me not distribute my power yet, just to kind of be clear here. Double check. Are we okay with that? Okay. So now I have that 3 secant squared theta now over, what's this going to be? 3 to the 4th. And then that's now going to be secant to the what? 4th power. So I distribute my power here, 2 times 2, and then times that 2. And now my constant will be 1/2 times, let's pull it out, 1 over 3 to the 3rd power. And then we're going to integrate, and then we have really 1 over what? Secant squared theta d theta. Is that true? Okay, double check. And then what's the reciprocal of secant squared theta? 1 over secant squared theta. What's this reciprocal here? Isn't that cosine squared theta? D theta? Is that true? And so the constant, though, is like 1 over 54. And then you integrate really cosine squared theta. Bless you. Now, how do you guys integrate cosine squared theta? Right? This is a trig integral. So I think that integral, don't you replace it with 1/2 what? Is it 1 plus cosine double theta? D theta? Is that what it is? Do you guys remember that half angle identity? So that's going to be now 1 over, as a constant, 108, the integral of 1 plus cosine double theta d theta here. And so you get that constant 108 if we integrate theta. Now, over here, of course, that's a u sub. Or a t sub, whatever you want to call it. I already know that's going to come out to be what? Derivative of sine is cosine. That's plus 1/2 sine double theta. Is that true? Okay, so if I distribute, we get 108 theta plus 1 over 216 sine double theta plus c. Okay, so now you go back and you say, but no, this is, this is all in terms of theta, and I have to do what here? I got to go back and use this relationship. I have to place this back in terms of u, don't I? I don't want to cut that. I want to copy it. Okay. Whatever. What is u again? 3. I guess I want to try that again. Let's copy. Okay. So this here, what do we replace sine double theta with? Sine double theta is going to become what? 2 sine theta cosine theta. Okay. Plus c. And now we say, okay, isn't that 108 theta plus, I think this is now going to be again 108 sine theta cosine theta plus c. Okay, because remember, we're going to have to do now, we're going to have to use u as 2 tangent theta. We're going to have to create that right triangle here. Because what that means is tangent theta will be what? U over 3. Opposite over what? Adjacent. Now, what does Pythagorean theorem say? This is going to be what? Is that u squared plus 3 by Pythagorean theorem? Okay. So remember, we need a few things, right? We need theta. We need what? Sine theta. And you need cosine theta. So if tangent theta is u over 3, doesn't that mean theta is the inverse tangent of u over 3 here? Right? So that's going to be replaced here. Inverse tangent of u over 3. Now, what about sine theta? Sine theta, by definition, is opposite over what? Hypotenuse. Is that true? And what's cosine theta? Adjacent over what? Hypotenuse. So this will be u over u squared plus 3, and this will be 3 over what? U squared plus 3. So what does that mean we really have? We have 108, not theta, inverse tangent u over 3, right? Plus 108 times what? 3u over u squared plus 3 what? Squared plus that c. And then what happens with this 3? Do you guys know? Because it's divisible by 3. 1 over 108 inverse tangent u over 3 plus, what is that? 3 goes into 108 how many times? I think it's going to be what? Is that 39 times? I don't know. 3 goes into 10 3 times. Is that right?
3, 6,
And then 18, 3 goes in 18 how many times? Is that 6 times? So we have u over u squared plus 3 squared plus that c here. But what was u to begin with? So you go all the way back to beginning. I think we took all our constants. What was u anyway? U was what? Wasn't u 2x to begin with? So that u is 2x. So wherever there's a u, you replace it with what? 2x. 2x. So here's your final answer. 1 over 108 inverse tangent 2x over 3 plus, forgot over here, 2x. Okay. So it looks like this is going to be plus 1 over, is that 18? X over 4x squared plus 3. Plus constant there. I don't know why that's bothering me. What's bothering me?
It should be right hand with a right triangle. U squared plus 3 squared into the...
Oh, that's where it is, right here. It's not a radical. It's 3 squared. Okay? So that's going to be now here. 3 squared is 9. So we get 9. That's what's bothering me. Okay. So it's 4 squared plus what here? Plus 9. It should be a radical? Pythagorean theorem?
I think so. Should be what-
I don't remember Pythagorean theorem. What's Pythagorean theorem? Isn't it going to be a squared plus b squared equals what? C squared. Am I missing a square root? Or is it no square root? Isn't this going to be, you say, here's A, here's B, here's what? Here's C? Is that true? You guys see what I'm saying? We're not solving for C. So that's going to be, by Pythagorean theorem, A squared, which is 3 squared. So we take the 3, we take the U, we square them, and we add them. Is that true? What do you guys get? Don't know. What's this? What's this length? Is that square root of what? U squared plus 9. So what would that mean if that's square root of u squared plus 9? You got the square root here, and so go put the what? Square root here, and that's 9. Square root, and that's 9. So now it just reduces the power, right? And there you go, 4x plus 9. I think it looks good. What do you guys think? Is that okay?
The square root.
Well, it is square root, but the square times the square root. Doesn't it get rid of that square root? So you have that u squared plus 9 here. Anyway, and put this in parentheses, because you have that constant there. Anyway, all right, we're fine. We just got to wake up with the Pythagorean theorem here. So here's kind of a quadratic version. And then I want to share with you guys another version. I don't think I did this one, but this is another quadratic version. Square root here, ladies and gentlemen, 5 minus what? 4x minus x squared dx. So remember we started this quadratic discussion. So from yesterday, what do we say the key was? How do you actually really do these things? From yesterday, the key. Yeah. So I'm going to have to write this 5 minus 4x minus x squared. I'm going to have to write it as a sum or difference, right? And you do that by completing the square. So you say, how do I go from here to here? You have to complete the square. And I do have a video for completing the square for what class? For 125. But you also have the 260 complete the square. If you guys remember, pre-calculus completing the square. Is pre-calculus in college the same as pre-calculus in high school?
No.
So I was doing with an email right now with the district telling them, hey, pre-calculus in high school is not the same as pre-calculus in.
I took pre-cal here before I took it in high school, and yeah.
It's not the same. In fact, calculus isn't even the same. Anyway. So how do we complete the square? If you guys remember, when I teach this in intermediate algebra, I'm going to say to you guys, I just rearranged those terms. You see this number, right? That's an A value in the quadratic formula, right? When you complete the square, so you guys know, if that A value is not 1, and that's the case here, A is not 1, you got to factor out the A. So you say, what do you mean? That leaves you now with x squared plus what? 4x minus 5. You got to factor out the A value. It doesn't matter if the A is 1. I'm sorry. if the a is not 1, it could be positive 2, it could be 4, it could be negative 2, it could be negative 4. In this case, a is just negative 1, because what you do now is right in here. This is where you what? Complete the square now. So that's probably something people have to go back and review, because you take the 4 now, it's that b value. So you take the 4 and you divide by 2, which gives you what? 2. You take that 2 and you square it, which gives you what? 4. That's your second step. You take the expression x squared minus 4x minus 5, okay, and that's your third step. If you guys remember that, complete the square process. And they really just say to you, if you guys remember, what do? Those first 3 terms, those first 2 terms, you leave them there, and then you do what? You add and subtract the number found in step 1. So you add 2, you subtract 2. Don't forget there's a negative 5. And I think something happened. I don't know where this 2 came from, but oh, there we go. Okay? So you're always going to use this number you found in step 1. You add it and you what? Subtract it. So it's like saying it's 0. And then what do you guys do, if you guys remember, for complete the square? Let me go back. You see those 2 terms and these last 2 terms? That's what you focus on. You factor, but you don't really factor. I'm sorry, I made a mistake. I'm not awake. It's a bad day. You don't use that number. You use what? See this here? Use the number in step 2. Yeah.
Shouldn't it be like x squared plus 4x?
X squared plus 4x, good. So we're going to add 4, we're going to subtract 4, okay? So it should be that plus 4. There we go. Okay, there we go. So now, ladies and gentlemen, we add it, we take it away. And then what I started to say here, you have to what now? Factor those first 3 terms and add the last 2. But you don't really factor. What do you guys do? You use the number found in step 1. That's a positive 2. So this means you have x plus 2 squared. This is what I mean by factoring. Okay, this is the number found in step 1, and then negative 4 minus 5 is a nice negative 9 here. Okay, you guys okay with that? Now, that expression we just found goes right in here. Well, you say where? That means that this is going to be negative 1 times x plus 2 squared minus 9, because that negative 1 factor, you're going back way over here to replace that. Don't know. Maybe use pink. This is what you just found. But when you distribute the negative 1 now, what do you guys get? Don't you get this? 9 minus x plus 2 squared? Okay, you guys know what I'm saying? So all along, that is under this radical. Okay? So that's under your radical. So what I'm saying is that this question really becomes the integral of the square root 9 minus x plus 2 squared over what? Dx. So these questions are now, I would say you now have really, what kind of question? What do you want to say this is? A trig what? Substitution question. But you say, no, no, not yet, not yet. I know, not yet. What do I mean by not yet? U sub, good. So it's first a U sub question, and then it's a trig sub question. So like all those other questions you guys had, right? So this would be my U. So you say U is going to be what? X plus 2. What does that mean? That means du dx is 1. That really means du is going to be what? Dx. 9 minus u squared over, what is dx?
1.
Du, right? Dx, because this is first a u sub question. And now, after you have this, this is now a what? What is this? A trig sub question. So, in our book, what case is this? Is that case 1 or case 2? Do you guys remember? In the book, what do we call that? Square root? 9 minus what? Oh, is that case 1? I think it's case 1. Is that true? That's case 1. What does that mean? U is, oh, what number is this? Isn't that 9? Isn't that 3 squared? So that means what? U is 3 sine theta. What is du? 3 cosine theta. What do I replace that radical 9 minus u squared with? Isn't that 3 what? Isn't that 3 cosine theta? Double check. Don't you replace that radical with that? I think so, ladies and gentlemen. So you might say, okay, does this integral then become 3 cosine theta? What is du? Du is 3 cosine theta d theta. Don't forget the d theta there. And so now this becomes 9 integral cosine squared theta d theta. That's a trig integral, because that's what trig sub generally does. It creates a trig integral. This trig integral, if you guys remember, you have to use what identity? Power reducing? 1/2 1 plus cosine double theta. Is that true? You guys okay with that? You can factor out the constant. So that constant is 9/2 integral 1 plus cosine double theta d theta. So like I've been saying, some of these integrals show up over and over and over again. Okay, what do you get when you integrate this? You guys know what you get? 9/2 theta, 1/2 sine what? Double theta plus c. So, you know, if I wanted to put some notes, I would say you're going to use what here? T sub for that integral. Is that right? T sub? Okay, distribute the 9/2. It looks like we have 9/2 theta plus 9/4 sine double theta plus c. And as you guys know, at this point yet again, you're going to have to replace that with what? 2 what? Isn't that 2 sine theta cosine theta again? So altogether, you got that 9/2 theta plus 9/2 sine theta cosine theta plus c, because this was a trig sub question where u is 3 sine theta. Is that true? U was 3 sine theta. Okay, you guys okay with that?
Can you scroll up?
So you might say, well, okay, well, what do I do with this? Well, what does this actually mean, right? This means that sine theta is u over 3. And I think we typically put that in purple. So I'll go back. This is u over 3. Is that true? And what is theta? Theta is inverse sine u over 3. So this is inverse sine u over 3. But then you have cosine here. Okay, so we have sine. The definition is opposite over hypotenuse. And then what does that mean about this side here? That's going to be the radical. Okay, square root of 9 minus u squared by Pythagorean theorem. 9 minus u squared, okay? So that means that my cosine curve is adjacent over my what? Hypotenuse. So you replace this with what? Square root 9 minus u squared over that 3. And ladies and gentlemen, now let's see, what do we have here, right? All together, we got 9 halves. Inverse sine u over 3. And then you're going to have, double check, plus that 1/2 u square root 9 minus u squared plus c. Is that true? Okay, see my point? Let's see. But what was u to begin with? What is u? Where was u?
X plus 2.
X plus 2. So if u is x plus 2, let's see what that final answer will be. 9 halves inverse sine x plus 2 over 3 plus x plus 2 over 2. And what do you think happens if I replace this here? Let's go back here. See this here? X plus 2, and then x plus 2 goes here. What do you think happens with that radical? That's the radical. 9 minus that x plus 2 squared. That's the original radical you have here. 5 minus 4x minus x squared, I believe, right? So 5 minus 4x minus x squared. That's what you get. You replace that u here. And these are what's called quadratic integrals. Does that factor of 2 go away? Double check. Are we okay with that? You got u. What was u again? I think u we have to say is x plus 2. Is that true? Anyway, double check. Double check, ladies and gentlemen, because I'm definitely not. Oh, yeah. All righty. Anyway. So just so you guys know, on the website, okay, I did put for you guys what? What did I put? I put the extra examples for you guys on the website. Is that right? Because what that now means here is something like this. Remember, there is more than one way to do some of these questions here. And where did I put the pen? There is more than one way. There we go. Like, for example, if I said to you, what if I have something like this? X minus 1, we have x squared plus what? 3x plus 2 dx here. Okay? You might be tempted to say to me, you know what, Mr. Judge? We have here a what? Quadratic. Is that true? Okay, you guys understand what I'm saying? You have a quadratic here? And that's true. Now, if you were to start to try to do this question here by using trig sub, right? You take that quadratic and you start to say, oh, I guess I'm going to do what? I'm going to use, whatever, right? Complete the square, and we try to use trig sub, you might run into some problems here. It might become harder. So, you have another approach really to some of these questions here. So it opens the door really to how do you approach this question here with what? An alternate approach. Now, here's what you guys want to recall here. Okay? Hopefully you guys can recall. Anybody remember partial fraction, decomposition? Do you guys know what I'm saying?
Yeah.
Partial fraction decomposition. I call it for short PFD. And I'm just curious, what is, if you've seen partial fraction decomposition in your life, right? What actually is that? Do you guys happen to know what it is? Right? And this is kind of what I'm dealing with in the middle. I see. Does not include the D grades. Sorry. Me. Hold on. So I'm just letting your guys' comments be here. Our high school pre-calculus experience Okay, sorry about that. I'm just sending this message out to our curriculum expert in the district. So, pre-calculus, you guys take this stuff in pre-calculus in high school? Partial fraction decomposition, anybody? And you go, oh my God, Mr. Judge, I've never seen partial fraction decomposition. What is this? What is partial fraction decomposition? Well, you're going to have a rational function here. Okay? Rational functions can be written. This is where partial fraction decomposition comes in. What PFD does, PFD writes a rational function, right, as the sum or difference of what? Quote unquote, simpler rational functions. Okay, simpler. You go, what are you talking about? Well, right in here, this is a rational function. What's a rational function, by the way, in case you guys forgot, right? A rational function we call R of x is P of x over Q of x, where both P and Q are what? Polynomial functions. Okay? So you have a numerator polynomial and you have a what? Denominator polynomial. Okay? So what I'm saying, and what's a polynomial, by the way? Do you guys know what a polynomial function is? So I'll give you the definition of a polynomial function, P. Polynomial function, P of x. Okay? It's any function that looks like this. You got a constant a1 and a variable x to the nth power plus a n minus 1, x to the n minus 1 power, all the way down to a1x plus a naught, okay? Okay. That's a polynomial function. So what you're looking at when I say this here, yes, the denominator is a quadratic. The numerator is a linear function. Okay. We could use partial fraction decomposition, okay, to write this as a sum or difference of two simpler rational functions. Okay, so here you go. And how you start the process, first of all, is go back down here. Remember this? I'm going to say this. Down there, you know what you guys want to do? Yes. Factor. Good. Outstanding. You want to factor that. Now you say, what do you mean? What is this factored? This is x plus 1 times x plus 2. Okay? So that fraction, when factored, is x plus 1 times x plus 2. Okay, so we factored that denominator. So far, so good? Okay. Now, if you guys don't recall, you're looking at this factor and you're looking at this factor. What you want to note is what kind of factors are both of these? You want to know what I'm going to say? What do you guys think? What kind of factors are those? Well, x plus 1. That's known as a linear factor. X plus 2. That's also a what? Linear factor. Okay, you guys okay with that? How do you know they're linear? What does it mean to be linear? The variable has a power for x being 1. If it's 2, it's what? Quadratic. If the highest power is a 3, it's a what? It's a cubic. Okay? So we also say the following here. You got two linear factors and they are distinct. What does that actually mean to be distinct? Do you know what that phrase means? They are different. They're not the same. So what I want to remark is that you have what's known as distinct linear factors. Okay? So for partial fraction decomposition, they'll take cases again, and this is for distinct what? Linear factors. So you want to consider cases here. Distinct linear factors. Now, here's what this means. For every linear factor, what do you guys use? Do you guys remember? You're going to use this a constant over that linear factor. And they describe a linear factor as ax plus b. Okay? So a is a constant here. Little a is also a constant. Little b is a constant. So what I want you guys to notice here is this. Here's what I'm going to do here. You see this here? I'm going to say this. Copy. We're going to write it this way. This is going to be equal to a over that first linear factor. So this is for the first one. Plus b over what? X plus 2. And then this is for the second one. So far, so good?
Yeah.
This is called case 1, when you're dealing with distinct linear factors. So for every linear factor, you replace it with a constant. You say, what happened to my A? Well, I mean, the book, well, let me put it this way. If you have 2, like in this case, yes, you can use B, Cx plus D. If you have 2, you could use subscripts like A1. Don't do that. A2. But anyway, this is your task now. You want to solve for what? The question is going to be what? What are the constants A and B? Okay? So what I want to remind you guys is you're going to now have to find the constants A and B. This is called partial fraction decomposition. And in theory, you study that in high school. I'm sorry, not high school, in math, in pre-calculus. Okay, partial fraction decomposition. Anyway. So how do we do this? You guys know how you do this?
Yeah.
How do you do it?
You multiply b by x plus 1, you multiply a by x plus 2.
Well, yeah, what you're doing, you're focusing on this right side, okay? And what you're focusing on doing is you want to try to do some what? Add these things. So you're really adding two fractions with different denominators. What's the shortcut? There's an algebraic shortcut. There's an algebraic shortcut. This is what that means. This is what? A times x plus 2 plus b times x plus 1. Don't forget you have to multiply by the denominator, x plus 1 times x plus 2. Do you guys remember that little algorithm? Do you guys remember the algorithm? The shortcut for adding unlike fractions? let me say this. I'm going to use different letters. A over B plus C over D, that's going to be AD plus BC over what? BD. That's your algorithm. Is that true? It's exactly what I just did. Now, you may notice and say this, logically speaking. You say, Mr. Judge, wait a minute. I see two fractions that are equivalent with the same denominator. Is that true? What does that mean has to be true? Okay? If A over B, I'm going to say this, equals C over B, then you know what that means? A has to be C. Is that true? What am I saying? Your denominator is the same. The fractions are equal. That means your numerators are the same. So that means x minus 1 equals A times x plus 2 plus B times x plus 1. And ladies and gentlemen, this really is what you're looking for. You're looking for this equation because you're trying to find the value of A and B. Does that make some sense? Okay, you guys okay with that? So then the question is going to be now, what is A and B? Or how do we find that? How do we find A and B? There's a couple of ways to do it. Couple of ways. Here's what I'm going to say. Focus on this one right here. You see this x plus 2? I'm going to make that 0. How can I make that 0, that x plus 2, 0? Let x be negative 2. If x is negative 2, wherever there's an x, replace it with a what? Negative 2. Okay? What that gives you is negative 2 minus 1 on the left side. This is going to be A times 0. Is that true? Plus B times negative 2 plus 1, which means negative 3 equals negative B. Is that right? What does that mean about B then? B equals what? 3. You found the constant. That's what you're looking for. Easy peasy lemon squeezy. How do you get A now? Well, go to the next linear term. How do I make the B value, well, not B, but how do I make that term 0? If you let x be negative 1 now, okay, don't you get this term to be 0 here? Is that true? Well, let's see. Let x be negative 1. When x is negative 1, here's what you get. Negative 1 minus 1 equals A, negative 1 plus 2 plus B, negative 1 plus 1. And that's going to be the 0 term now. So negative 2 is going to be what? A. Is that right? Double check. Is that true? What did you guys just find? A and B, the constants. So A is negative 2. You go, what do you mean A is negative 2? Go all the way back. What is A? What is B? 3. Okay. Here's what I'm going to say to you guys, because we're almost done. All the work is here. What this means, I'm going to switch my order. You have 3 x plus 2 minus 2 x plus 1. What are you supposed to integrate? This integral on the right is easier to do. Do you guys agree with me?
Yep.
You say, well, what do you mean? Well, take out your constant 3, right? Integral of a sum, a difference is difference of integrals. Pull out that constant, 1 over x plus 1 dx. I'm saying these are easier to do. Because this is now going to be what? 3 natural log absolute value x plus 2 minus 2 natural log x plus 1 plus c. So the reason you care about partial fraction decomposition, generally speaking, is because you can write now any rational function as a what? Sum or difference that consists of easier rational functions that you can integrate. So I did want to get to this topic as soon as possible so that you can get as much practice as soon as possible on really, partial fraction decomposition. Because remember what I said before about the course. What I teach you is like 10% new. The rest is 90% old. It's based on the past. So partial fraction decomposition is based on your what? Past. Now, do I have those videos too for you guys if you want to see some? Do you guys notice I updated that with past lectures on PFD? What's PFD stand for? Partial fraction decomposition. What does IBP stand for? Integration by parts, not ibuprofen. Right? So we started the partial fraction decomposition because, some of these questions can be done by trig sub, but they can also be done probably more effectively by using what? Partial fraction decomposition, and that's the transition. So, in your book, let's see if I can find it. 262. Oh, come on. Oh, yeah, we do have some partial fraction decomposition. Is that right? Yeah. So I already have that there for you guys, and I wanted to start that. But those videos are on my website as well. You guys can look that over too. Of course, we're going to continue with more examples tomorrow on partial fraction decomposition. But look over some of those questions if you want. And we started PFD. You may want to put extra time in reviewing that because the real work is finding the constants. And you're going to see that in the future here. So, okay. So we'll see you guys later. I'll upload this video when I get home as well. And